Good morning. Today, I'd like to remain off topic for a while longer and go back to these differential equations of motion that we were talking about. For simplicity, I'm going to start with the Newtonian problem, which worked out to be just this differential equation. If we assume that r takes on its minimum value so that u takes on its maximum value when theta is 0, then we figured out that the solution to this equation can be written in this format. Remembering, of course, that u is 1 over r, so that r is 1 over u. X is r cosine theta, 1 over u cosine theta, and y coordinate is r sine theta, 1 over u sine theta. In order to test our numerical method, I'm going to make up a problem whose solution I already know. I'm going to let u equal 1 over 9 times 1 plus 1/2 cosine theta. That means that r will be 9 divided by 1 plus 1/2 cosine theta. The eccentricity will be 1/2. Taking the first and second derivatives of u, adding the second derivative of u to u results in 1/9. So my differential equation is going to be second derivative of u plus u equal 1/9. The 1/9 plays the role of the gm over h squared. Since I have a formula for u already, u at 0 is 1/9 times 1 plus 1/2 cosine 0, which works out to be 1 over 6. This is the maximum value of u corresponding to a minimum value of r equal to 6. I can write my differential equation as second derivative of u plus u equal 1/9 with initial conditions u at 0 equal 1/6 and u prime at 0 equal to 0. So in the same way as before, I can write my second order differential equation as a vector differential equation. The derivative of vector y is the vector that has y2 as its first component and 1/9 minus y1 as the second component. At theta equals 0, the value of the solution vector is 1 over 6, 0. In what follows, I'm going to use my Euler method routine to solve these equations numerically, at least approximately. I'm going to solve it first with only a few subintervals, and then more, and then considerably more, and we'll see that the results that we get improve with the number of subdivisions. Also, what I'm printing out is a plot of theta values versus the corresponding value of y1, the corresponding value of u. The purple graph is the computed solution from my Euler method, while the other graph is the exact value of the u quantities as calculated by my computer. As you can see, these two graphs are roughly similar looking, but they're not very close to each other. Here, I've increased the number of subintervals to 100, and you'll notice that the agreement between the two curves is considerably improved. Here, I've increased the number of subintervals to 1000, and as you can see, the agreement between the computed solution and the computer version of the exact solution is better still. This is how things should be. Before going on to look at the orbit, I do want to make a couple of comments, though, concerning the representation of pictures on a computer. Very often, when people draw up graphs of orbits and things of that nature, they'll plot a point, they'll increase the position by a little bit, they'll plot another point, connect those 2 points with a straight line, and then continue on this process. I want to think about what would happen if you did that, but your calculations were not exactly perfect. What if you're not exactly where you think you should be, but you carry that procedure out anyway? If there were no errors at all, you would go around theta from 0 to 2 pi, and you would end up with a picture that didn't really look much like an ellipse, but that's just because of this connect the dots with a straight line business. Also, what if you ran this for more than theta equals 0 to 2 pi, more than one orbit? What would happen then? So I'm thinking that because of errors in the calculations, you're not exactly ending up where you should be, although you are getting points that are basically on the ellipse that you're interested in. So starting here, I might, in an exact world, want to end up on the y-axis, but in reality, because of errors in the calculation, I end up slightly displaced from it. Ideally, I would be on the y-axis, and I might get a point on the negative x-axis. But again, because of errors, I land slightly at a different place. Likewise for this, I've almost completed one orbit, but I want to continue this line of thinking. Ideally, I would go around 0 to 2 pi and end up right back where I started, but what's the error going to do to that? I'm going to end up at a place that's not exactly where I should have been. This is going to continue as we go along, and I'll end up with some sort of bizarre etch-a-sketch looking shape here. In my program, I'm going to increase the range of theta values to correspond to 10 orbits, and then I want to look at what happens when I calculate this computed solution for various values of the number of subintervals, connecting the dots with line segments like this. This is with 200 subdivisions. As you can tell, this isn't very good at all. The scale of the thing is all wrong. So I'm going to increase the number of subdivisions to 2,000 and see what happens. With n equal 2,000, I get horrific results. Let's take it up to 3,000. The n equal 3,000 is somewhat better, but obviously this is still scaled much too big. So I'm going to look at n equal 5,000. I'm going to do finally one last example of this. I'm going to do 1,000,000 steps. Finally, with 1,000,000 steps, I get something that looks reasonable. The closest point to the origin, about there, is supposed to have x coordinate equal to 6. Here is x equal 5, so x equals 6 is about there. So this seems about right. So thing number one, beware of the jagged edge thing. Also, Euler's method works in a certain sense, but you have to make the number of subdivisions so big that it begins to chew up a noticeable amount of time to run the program. Not only that, there's another worry that we haven't thought of. In any kind of floating point calculation on a computer, there are going to be rounding errors. The more you compute, the more rounding error you're going to get. So it's a bit of a concern. I don't really want to go around using n equal 1,000,000 or some such value because I worry that the rounding error is going to spoil my accuracy. We'll address this in the next video, so we'll remain a little off track for a while longer. In the meantime, I hope everybody has a good day, and I'll talk to you again soon.